All right, this is Unit 2, Lesson 2, Limits Involving Infinity. So if we are dealing with limits involving infinity, so finite limits as x approaches positive or negative infinity. So the symbol infinity doesn't actually represent a real number. It just describes what a function does as it approaches, as it goes further to the right for positive infinity or further to the left for negative infinity. So basically, if I'm looking at this function right here, as x approaches positive infinity, we can see it gets closer and closer to 0, but it actually never touches 0. The same thing if it's going towards negative infinity. So this actually comes up and goes, it gets closer and closer to 0, but it never actually touches. So that's actually called a vertical or a horizontal asymptote. So basically here's an asymptote right here at the 0. Basically means it never, that limit never touches that particular point on the graph. It won't cross it. It won't touch it. It might get super close to it, but it'll never actually touch the function. Okay. So line y equals b is a horizontal asymptote of the graph of a function y equals f of x. If either the limit of f of x as x approaches infinity equals b, or the limit as x approaches negative infinity of f of x equals b. So the graph of x, f of x equals 2 plus 1 over x has the single horizontal asymptote y equals 2, because it gets, as this approaches infinity, it gets closer to 2, but it'll never touch. Same thing with negative infinity, it gets closer to 2, but it'll never touch. Okay. So a function can have more than one horizontal asymptote. So if we look at example number 1, this actually has more than one horizontal asymptote. So use graphs and tables to find the limit of f of x as x approaches infinity and the limit of f of x as x approaches negative infinity, and identify all the horizontal asymptotes of f of x equals x divided by the square root of x squared plus 1. So if I'm solving this graphically, okay. So this is graphically, this is what this looks like. So you can see up here at the top, this red line. This red line, it gets super close to it, and it looks almost like it's touching, but it's not actually touching. So those are going to be my horizontal asymptotes of y equals 1 and y equals negative 1. You can actually see here, as x gets larger, it gets closer and closer to 1, but it doesn't actually touch. Same thing when you're going towards negative infinity, it gets closer and closer to negative 1, but it never actually touches. So I can confirm that numerically, obviously, by looking at the tables. That's what these are up here. So basically confirms that there are two horizontal asymptotes, one at negative 1 and one at 1, where the function will go in between them, but it'll never actually touch those points. All right, the sandwich theorem revisited. So as we learned last time, the sandwich theorem basically stated if I take, or it's sandwich or squeeze, if I have a function and I don't know what the limit is, I can squish it between two, like a sandwich. And if their limits are the same, then the limit in between them is the same. So example number 2, finding a limit as x approaches infinity. So I want to find the limit of f of x as x approaches infinity for f of x equals sine x over x, or divided by x. So here's what this looks like. It's kind of this like cool graph. So I can solve graphically and numerically. The graph and table of values in figure 2.11, which is right here, suggests that y equals 0 is a horizontal asymptote of f. So you can see 100, 200, 300, 400, it's closer and closer to 0. This is negative 7.4 to the negative 10 to the negative 5th power. 7.8 times 10 to the negative. So it gets closer and closer to 0. These are just getting larger. These just are becoming larger decimals. You can confirm it analytically by using the sandwich theorem. So we know that negative 1 is less than or equal to sine x, which is less than or equal to 1. So for x is greater than 0, we have negative 1 over x is less than or equal to sine x over x is less than or equal to 1 over x. Okay, so the original function was sine x over x. So I just divided the negative 1 and the positive 1 on either side by x to make it similar. So therefore, by the sandwich theorem, it's 0 because limit as x approaches infinity, negative 1 over x equals the limit of sine x over x as x approaches infinity equals the limit of 1 over x as x approaches infinity, which all equals 0. So since sine x over x is an even function of x, we can conclude that it does equal 0. So limits at infinity have properties that are similar to those with finite functions or finite limits. So properties of limits as x approaches either positive infinity or negative infinity. So if L, M, and K are real numbers and the limit of f of x as x approaches plus or minus infinity equals L, and the limit of g of x as x approaches to plus or minus infinity equals M, then we have the following 6 rules. So the first one is the sum rule. So basically, I take the limit of f of x plus the limit of g of x, both as they're approaching the plus or minus infinity. That equals L plus M. Okay? Difference rule, I can subtract them. L minus M. Product rule, I multiply them. I multiply the limits. Constant multiple rule, I can multiply any limit by a constant k, and I'm multiplying k times that limit. The quotient rule, so I would take L over M, provided M cannot be 0. Again, can't divide by 0. Bad things happen in the universe. When you divide by 0, don't do it. Power rule, if R and S are integers, S does not equal 0, then f of x raised to the rs power equals that limit raised to the r divided by s power, provided that that limit L raised to the r divided by s is an actual real number. Because if it's not a real number, then it doesn't matter. So we can use theorem 5 and to basically find limits of functions with complicated expressions. So looking at example 3, using theorem 5, I can find limit x, 5x plus sine x over x as x approaches infinity. So I can notice that 5x plus sine x, I can break that down. I can use the sum rule here, and I can use the quotient rule as well if I wanted to, but I probably won't end up doing that. So 5x plus sine x over x equals 5x over x plus sine x over x equals 5, because the x's cancel, plus sine x over x. So this limit of 5x plus sine x over x as x approaches infinity equals the limit of 5 as x approaches infinity plus the limit of sine x over x as x approaches infinity. Well, we already know that this is 0, this sine x plus x. We found that in example 2. So the limit of 5 as x approaches infinity is 5, so 5 plus 0 is 5. Okay. All right, so infinite limits as x approaches a. So if the value of a function f of x outgrows all positive bounds as x approaches a finite number a, we say that the limit f of x as x approaches a equals infinity. Okay, so if the values of f become large and negative, or exceeding all negative bounds as x approaches a, we say that limit f of x as x approaches a is negative infinity. So looking at f of x equals 1 over x, page 70, we can see that the limit of 1 over x as x approaches 0 from the right equals infinity, and the limit of 1 over x as x approaches 0 from the left is negative infinity. So there's a vertical asymptote there. So if you look at, go back to it, this limit again, this one up here. Okay, so if I'm looking at this graph up here, as the limit 1 over x approaches 0 from the right, goes towards infinity. This one. So I'm approaching from the right, it's going towards infinity, goes up forever. I'm approaching 0 from the left, it's going towards negative infinity forever, but it never actually touches this the y-axis. Okay, so there's a vertical asymptote at 0, just like there was a horizontal asymptote at 0. So the line x equals a is a vertical asymptote of the graph of a function y equals f of x if either the limit f of x as x approaches a from the right is positive or minus infinity, or the limit of f of x as x approaches a from the left is positive or negative infinity. Okay. So example 4, finding a vertical asymptote. So I can find vertical asymptotes of f of x equals 1 over x squared and describe the behavior to the left and right of each vertical asymptote. So the values of the function approach infinity on either side of x equals 0. So the limit of 1 over x squared as x approaches 0 from the right is infinity, and the limit of 1 over x squared as x approaches 0 from the left is negative infinity. So I can actually graph this. So that's what this graph looks like, this 1 over x squared. So you can see as it approaches, so I'm coming from this way, as I approach from the right, I skyrocket to infinity as I go. And if I approach from the left, I'm also going towards infinity. Okay, but I never touch this vertical asymptote right here in the center. Like I can scroll out and you can see like that's super small and it just looks like a really dark line. Scroll in a little bit. But you can see that they get closer and closer to the 0, but they never actually touch. Okay, so I could go up forever. Look, I'm at 40. You can notice that they're getting closer to each other. But if I scroll in even more, you can see that they're still further, like they're still far enough away from each other. Okay, so they never actually touch. Okay. So you can see that there is a vertical asymptote at x equals 0. Okay, so we can also say that limit of 1 over x squared as x approaches 0 is infinity. We can make no such statement, though, about 1 over x. We can't, that's not a true statement. Okay, so example number 5, finding vertical asymptotes. The graph of f of x equals tangent of x equals sine of x over cosine of x. So this is what the graph of tangent of x looks like. It's these fun, like they stop. So there's actually vertical asymptotes at each of these spots. Okay. So one at each point where the cosine is 0. So whenever cosine 0, there can't actually be a graph there because, again, if you divide by 0, bad things happen. So if a is an odd multiple of pi over 2, then the limit of tangent of x as x approaches a from the right is going towards negative infinity. So I'm going from the right, yep, yep, yep. See? As I approach a from the left, I'm going towards positive infinity. So I'm going loop, loop, see? Positive infinity, okay? So you can see that in this figure right here. So that's where this break is each time. Anywhere that cosine is 0 for tangent, that's where they're going to have a vertical asymptote. So you might think that the graph of a quotient always has a vertical asymptote where the denominator is 0, but it's not always the case. So for example, we observed in section 2.1 that the limit of sine of x over x as x approaches 0 is actually 1. Okay. So there's not necessarily always a vertical asymptote. Usually is, but not always. Okay. So N behavior models, for numerically large values of x, we can sometimes model the behavior of a complicated function using a simpler one. So using a function that we kind of already know or know what it's going to look like, I can figure out what it's actually going to, what the actual function is going to look like. Okay? So they act essentially the same. So example 6, modeling functions for the absolute value of x large. So I'm going to let f of x equal 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6, and g of x to equal 3x to the fourth. Okay. Show that while f and g are quite different for numerically small values of x, they are virtually identical for large ones. Okay. So I can solve this graphically. The graphs of f and g are quite different near the origin, but they're virtually identical on a larger scale. So here's the close-up version. So you can see the blue is the f of x, and the black line is going to be my g of x value. So, but if I scale out, so this is negative 20 to 20 by 100, negative 100,000 to 500,000. They look almost exactly the same. So I can confirm analytically, basically algebraically, that this actually works. So we can test the claim that G models f for numerically large values of x by examining the ratio of the two functions as x approaches positive, negative infinity. So we find that the limit of f of x over g of x is, as x approaches positive, negative infinity, equals the limit 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6 divided by 3x to the fourth as x approaches positive, negative infinity. Okay. So when I do this, when I simplify it, 3x to the fourth divided by 3x to the fourth is 1. 2x cubed divided by 3x fourth is 2 over 3x. 3x squared divided by 3x to the fourth is 1 over x squared. Negative 5x over 3x to the fourth is 5 over 3x cubed. And then 6 over 3x to the fourth is 2 over x to the fourth, which gets closer and closer to 1. Okay. So convincing evidence that f and g behave alike for the absolute value of x large. So end behavior model. The function g is a right end behavior model for f if and only if the limit of f of x over g of x as x approaches positive infinity equals 1. And the left end behavior model for f if and only if the limit of f of x over g of x as x approaches negative infinity equals 1. So if one function provides both a left and right end behavior model, it's simply called the end behavior model. So if it shows both, we're not going to classify it as right or left. So therefore, g of x equals 3x to the fourth is an end behavior model for the f of x function. Because they both equal the same thing. So in general, g of x equals a sub n x to the nth is an end behavior model for the polynomial function f of x, as long as it doesn't equal 0. So overall, the end behavior of all polynomials behave like the end behavior of monomials. So basically what this says is I can take the first value of this function, the f of x function, and that becomes my g of x function, which helps me determine the end behavior for the model. So this is a key to the end behavior of rational functions, which we're going to see in example 7. So I'm finding end behavior models for a and b. So for a, I have 2x to the fifth plus x to the fourth minus x squared plus 1 over 3x squared minus 5x plus 7. So the first thing that I want to do is I can notice that 2x to the fifth is an end behavior model for the numerator of f, and 3x squared is 1 for the denominator. So basically, I took these first parts of my polynomial, and that became my end behavior model for my f of x, for the numerator and the denominator. And then I just simplified them. So 2x to the fifth over 3x squared becomes 2/3 x to the x cubed. That's my end behavior model for f. So same thing I can do for g of x. I have 2x cubed over 5x cubed. I simplify them. It's 2/5. Okay, so that's the end behavior model for g of x. So basically I'm taking the first section, simplifying it. That becomes my end behavior model. Okay, so I can notice in example 7b that the end behavior model for g y equals 2/5 is also a horizontal asymptote of the graph of g. While in A, the graph of f doesn't have a horizontal asymptote. We can use the end behavior model of a rational function to identify any horizontal asymptotes at the same time. So if there's no x value, there is no horizontal asymptote. If there is no x value, So like in B, that's my horizontal asymptote. If there is, there's no horizontal asymptote. Okay. So functions right and left end behavior models don't need to be the same function. So for example, 8, I'm finding end behavior models for f of x equals x plus e to the negative x. And I want to show that g of x equals x is the right end behavior model for f, while h of x equals e to the negative x is a left end behavior model for f. Okay, so solution. On the right, the limit of f of x over g of x as x approaches infinity, because I'm going from the right. Okay, so x plus e to the negative x over x equals 1 plus e to the negative x over x. So x cancels, becomes 1. Equals 1 because the limit of e to the negative x over x equals 0. Okay. On the left-hand side, so as x approaches negative infinity, I have my limit x plus e to the negative x over e to the negative x equals x over e to the negative x plus 1, this cancels, equals 1 because the limit of x over e to the negative x as x approaches negative infinity is 0. So as I'm coming from the left, it's approaching 0. As I'm coming from the right, it's approaching 1. Sorry. They're both approaching 1. So there's 1 right there. So as I'm coming from the right, so I'm coming from the left, I'm approaching 1. As I'm coming from the right, I'm approaching 1. All right, seeing limits as x approaches positive or negative infinity. So we can also investigate the graph of y equals f of x as x approaches positive negative infinity by investigating the graph of y equals f of 1 over x as x approaches 0. That's what that graph looks like, this 1 over x. And we said before there's a vertical asymptote at 0 and a horizontal asymptote at 0. Just a reminder. So for example 9, we can use substitution to find the limit of sine 1 over x as x approaches infinity. So in figure 2.15a, which is this one, okay, it suggests that the limit is 0. Indeed, by replacing the limit of sine of 1 over x as x approaches infinity by the equivalent limit sine of x as x approaches 0 from the right equals 0, we find that the limit of sine of 1 over x as x approaches infinity equals the limit of sine of x as x approaches 0 from the right equals 0. So this is what this graph looks like. And that's sine over 1 over x. And this is what sine over x looks like. So we can see, like looking at this, it suggests that the limit is 0. There's this crazy thing right here. So if you want to look at it, that's what this graph looks like far away. I get closer. It does these like crazy things. Like this whole thing is blacked out because it just got, as I scroll in closer and closer and closer, you can see that these are each becoming individual lines. So it just does random weird things. So the solution is 0. Because as this approaches 0 from the right, I get 0 because it's going to 0. Okay. And that is the end of Unit 2, Lesson 2.